Hey everyone. So today begins our second unit, and our second unit is focusing on derivatives. Now, as with the beginning of any new unit, this particular lesson may feel at first a little confusing, but what I want you to realize right off the bat is we're not really doing a whole lot new today, okay? Here's the thing. A derivative, that term, refers to the slope of a tangent line. Well, we've been finding slopes of tangent lines for the last, week and a half? We've been using limits to find the slope of tangent lines, okay? But really, we've been using limits to find derivatives. That's all a derivative is it represents the slope of tangent line, okay? In the last week, we've used limits to calculate derivatives. We just haven't called them derivatives, okay? And so everything that you've done with limits, that's why we started with limits, everything you've done with limits, you're still gonna do with derivatives, okay? So I'm hoping in that sense, the work we do, the math we do today should feel very familiar. What you have to wrap your head around is just some of the vocabulary, some of the ways of speaking that we're going to talk about today. So with that quick little introduction, let's dive in here to what we're going to do. So we used two formula to determine the slope of a tangent to the curve and the instantaneous rate of change. These limits are called the derivative. The derivative of a function f at a particular number a is denoted by f prime of a, okay? Or we could say the derivative of f at a, f prime at a, and is given by the following. Well, f prime at a could be the limit of f of a plus h minus f of a all over h, where h is approaching 0. Or it could be f prime a is the limit of f of x minus f of a all over x minus a, where x is approaching a. Those two formulas you have been using over and over and over again in the last couple of days, okay? So there's nothing new in that sense. Now we're just calling it a derivative, okay? And that assumes that the limits exist. Okay, so the derivative can be interpreted as the blank of a tangent. Well, you know that, it's the slope of a tangent. The tangent line to the curve, y equals f of x, at the point a comma f of a has the slope of f prime at a, okay? So this guy here represents the derivative at point A. It represents the slope of the tangent at point A. And that's what we've been doing over and over and over again for the last few days. Okay. The derivative can also be interpreted as the instantaneous rate of change, and this is something we've also already talked about. The instantaneous rate of change of y with respect to x when x equals a equals the derivative at a. Okay, the derivative of f at a, f prime at a. Okay, in particular, if s of t is the position function of an object at time t, then the velocity of the object at time t equals a is given by s prime of a. So essentially, the big message here is the velocity of an object is the derivative of its position function, okay? So in other words, v of a will equal s prime of at a, okay? Okay, so for f of x equals 2x squared minus 4x minus 1, determine f prime at 4. So what are we being asked to determine? Well, we're being asked to determine the derivative of the function at 4. What does that mean? We're being asked to determine the slope of the tangent line for 2x squared minus 4x minus 1 when x equals 4. That's what this f prime at 4 is asking you to do. That's what the derivative means, okay? Well, there's nothing new here then. we can do that. I could have asked you that on your test. So now we're going to call it, though, f prime at 4, okay, and we're going to keep that in the front, equals the limit of f of x minus f of 4 all over x minus 4 as x approaches 4. Okay, so I know 2 of x is 2x squared. Sorry, I know f of x, that was my bad. F of x is 2x squared minus 4x minus 1. And I know x will be 4. I got to plug 4 into here to get f of 4. Okay, when I do that, I get out 15. Okay. Now, we're just going to clean this up. I've got 2x squared minus 4x minus 16 all over x minus 4. I want to take the limit, but I can't do direct substitution right now. I can't do direct substitution because x minus 4 is on the bottom, and that creates a non-permissible value. I can't plug in 4. So now I'm going to try and simplify this so that I can try substitution into the simplified version, just like I've always been doing. Okay, so what I've done now is I factored out the 2, and now I'm going to try and factor the trinomial. Two numbers that multiply together to give me -6 and add together to give me -2 would be -2 and -4 and +2. -4 and +2. Okay, so I go ahead and factor that. And now my x minus 4s will divide each other out. I've gotten rid of my problem. Okay, so that leaves me with 2 times x plus 2, and now I can substitute 4 in there. So if I substitute 4 in there, I get 4 plus 2 is 6 times 2 is 12. So f prime at 4 is 12. That means if I was to draw this function out, first of all, there exists the point 4, 15. And at that point, 4, 15, if I was to draw a tangent line, the slope of that tangent line would be 12. That's what we just figured out when we're saying the derivative of the function at 4 is 12. Okay? That's what that statement means. Okay? Okay. So for f of x equals 2x squared minus 4x minus 1, write two interpretations of f prime at 4 equals 12. Okay, so here we go. We could say the slope of the tangent to f of x at x equals 4 is 12. That's what I just said to you, right? If you were listening. Or we could say the instantaneous velocity at t equals 4 is 12. Okay? Okay, now, for f of x equals 2x squared minus 4x minus 1, determine f prime at x. So now I'm asking you for the general equation. Okay, and we've done this before. When we were dealing with limits, we created an equation first, and then we started plugging numbers in. Okay, so that's what I want you to do here. So for the general point x comma f of x, and use this formula to determine the derivative at 4 and the derivative at 9. Now, we already know the derivative at 4, but we want to just test the equation that we are creating, okay? Okay, so I'm going to find the limit going the other way, though. I'm going to use the method 2. So I'm going to go f of a plus h minus f of a all over h, where the limit is when h approaches 0, okay? Okay, so I plug in a plus h into my x's. So I've got 2x squared minus 4x minus 1. Okay, so all of this, I just want to switch colors here so that you can, so all of this right to there was this. Okay, and then I'm going to minus f of a, so I minused f of a. Okay. Now, I'm going to have to clean this up. So I'll distribute my negative, and then I can multiply, I can do my a plus h all squared. That's going to be a squared plus 2ah plus h squared. I can distribute the 2 then, and I can distribute the -4 into the a plus h. So you have a little bit of cleaning up to do here. I'll give you a chance to do that, or you're going to give yourself a chance to do that by pausing me. Okay. So I've done that multiplication. I've brought the -4 in, and I brought the negative in there. Now I'm going to bring the 2 in and combine like terms. Okay. Now my 2a squares are gone, and I can factor out an h. Now remember, the whole purpose of everything I'm doing right now is to get rid of the problem. The problem is there's an h on the bottom, so the fact that I'm now at a point where I can factor an h out, that's going to get rid of my problem and allow me to substitute 0 in for h. Okay, so, whoops, sorry. Okay, so my h comes out, and I'm left with 4a plus 2h minus 4. When that approaches 0, my 2h will go, so I'm left with 4a minus 4. Okay? Okay, so this represents the equation, the general equation for the derivative at any point, any value for a or any value for x for the original guy. Okay? So now I'm going to plug in 4 and I'm going to plug in 9. Look what happens when I plug in 4. 4 times 4 is 16 minus 4 is 12, which is exactly what we got on the previous question. And then if I did 9, 4 times 9 minus 4, I get 32. Okay, so what we're saying is the slope of the tangent at x equals 4 is 12. The slope of the tangent line at x equals 9 is 32. Okay? And this is the general equation of the derivative for 2x squared minus 4x minus 1. Now, I didn't really need to switch that to a's. I could have just left that all as x's. But it doesn't matter. Okay. Draw the graph of f of x and determine the domain for f of x and for the derivative of f of x. Is f differentiable everywhere? Okay, so we're going to draw these two functions. So my original function, which was the x squared function, is my blue guy. Okay, and then my derivative is the red guy. Now, what does differentiable mean? A function is said to be differentiable if its derivative exists on each point, at each point on the domain. So if I go through the domain of my blue graph, my original f of x, okay, there is a derivative for every one. Now, I want you to be able to read what you're seeing here. So if I looked at the domain of the blue graph, the domain exists, it's a member of the reals, right? Now, I want to make sure you're reading this proper. The red graph represents the derivative, okay? So take a look at this. At x equals, let's do one that you can see here. At x equals 0, okay, the derivative is -4. You see that? Because I'm reading the y value off of the red line. The red line is my derivative function. So at x equals 0, if I was to draw a tangent line there, I would get a slope at -4. At x equals 1, right here, my slope is 0. Well, that makes perfect sense because I'm right on the vertex there. Okay, at x equals 2, my slope is 4. Okay, that's how I'm reading this. So this red line tells me the derivative for every point along the original function. Okay, now the blue line, x is a member of the reals. The derivative, x is a member of the reals. So we say that f is differentiable everywhere. Okay, we say that f is differentiable everywhere. Okay, so the domain for f of x is -infinity to infinity, and the domain for the derivative is also -infinity to infinity. F is differentiable everywhere. Okay. All right. If you're curious, the derivatives, you can calculate derivatives on graphing calculators just while you're doing all of this stuff. Obviously, you know, right now you're looking at a page of work for a question, or a half page of work. You can't just do this in your graphing calculator. That's why your graphing calculators aren't allowed. But that being said, while you're doing your homework, it's a great way to check your work. So instructions are there on how you want to do that. Okay, if g of x equals the root of 2x minus 1, determine the derivative of g of x. So determine g prime at x. So again, I want to come up with the formula. So I'm going to use limits to achieve that. So the derivative of g of a equals the limit as h approaches 0. And again, it's just a plus h being plugged in and then the original guy. So I've got the root of 2x minus 1, so that's 2a plus h minus 1, minus the root of 2a plus h. Now again, my problem is the h. I can't do direct substitution right now, so I'm going to have to do something to this. Well, in all of the tools we talked about in Unit 1, the only thing I have available to me at the moment is maybe try to rationalize the numerator. So I'm going to multiply by the conjugate. So I'm going to multiply this by root of 2 times a plus h minus 1 plus the root of 2a minus 1. Okay, so that's going to create a nice big mess for a minute, but that's going to give me, oh, let me switch to a different color. That was kind of stupid. That's going to give me, oh, you know what? I'm probably in the way here. Let me take myself out for a sec. That's going to give me this times this, which would just be 2a plus h minus 1. And then this guy will give me the positive version of those guys multiplied together, and then this guy will give me the negative version of those guys multiplied together, so they will add to 0. And then I'll be left with negative bracket 2a minus 1. Okay. On the bottom, I'm just going to leave that in factored form right now, because remember, the whole purpose was to get rid of the problem. Okay. Now I have to distribute my negative. My 2a's are going to go and my 1's are going to go, and I'll be left with just 2h, which gets rid of my problem because my h's can now divide each other out. Okay, so this guy's gone and this guy's gone, and now I can have h approach 0, no problem. When I have h approach 0, well, this gives me 2a minus 1, and so the root of 2a minus 1 plus the root of 2a minus 1, an apple plus an apple is 2 apples, so that's going to give me 2 root of 2a minus 1's. And then my 2 on top will divide out with the 2 on bottom. And so I'm left with 1 over the root of 2a minus 1. So this guy represents the derivative for g of x. Okay. Now we're going to graph that. So again, my blue guy is going to be the original, and my red guy will be the derivative. And we're going to look at whether g is differentiable everywhere. So go ahead and graph that. You should end up with a picture that looks something like this. And now we want to talk about this conversation, is g differentiable? Well, the answer is no, and the answer is no because my domains are actually slightly different here. Remember that the definition of differentiable is that the derivative exists during the entire domain of the original. But for this guy, we actually end up with a vertical asymptote at 1/2. So take a very close look at the difference here, right? In the original, x could be 1/2, but in the derivative, x can't be 1/2. And because of that, g is not differentiable, okay? So g is not differentiable everywhere. Think about open versus closed intervals. The derivative doesn't exist at the endpoint. There are an infinite number of tangent lines at that endpoint, okay? Okay, show that f of x equals the absolute value of x is not differentiable at x equals 0 algebraically and graphically. Okay, so we're going to start with the algebra first. So what I'm looking at is I'm looking at the derivative on the left side. And so how to do that is, again, this should be x plus h minus x, right? So I'm plugging in 0 for my x. So this is my x plus h minus x, but I took the negative version of that. So I'm looking at it from the left. And when I do that, I get negative h over h. And so that will equal negative 1. Okay. Now I'll look at it from the right side. So from the right side, I would be the positive version. So that would just give me 0 plus h, not negative 0 plus h. That's going to give me h over h. H over h is 1. Okay. Now, some of you can look at this and say, yeah, but I could never have plugged 0 in either, which means at 0, there is no derivative, right? So we can say the derivative of 0 does not exist. And so this proves algebraically that it's not differentiable, okay? Now, graphically, you're getting something that looks like this. So I've graphed y equals the absolute value of x. On the left, I see that the derivative will always be negative 1. On the right, I see the derivative will always be 1, but then I don't have anything at 0. Okay? The derivative doesn't exist at a point in the domain. If you look at the graph, the slopes from right and left of 0 are different. Okay? So again, it is not differentiable. Okay, so in general, the derivative can be seen as a function of x. Given a function f, the derivative of f is the function f prime, and it's defined by the limit, as h approaches 0, of f of x plus h minus f of x all over h. A function is said to be differentiable at x equals a if the derivative at a exists. A function is said to be differentiable on an open interval if it is differentiable at every number on that interval. So there has to be a derivative for every number across that particular interval in order for the function to be differentiable, okay? Okay, the graph of y equals f of x is shown below. State the values of x where the function is not differentiable. Okay, I would want your eyes to dart to a few different places. I'd want you to look at x equals 1, at x equals 3, and at x equals 5. Now, in each of these, the left side derivative and the right side derivative do not equal. Okay, so you must state this as part of your answer. You must say the derivative on the left of 1 versus the derivative on the right of 1 is not the same. Okay. Okay, so a function is differentiable at a point if one tangent line can be drawn. Functions whose graphs have corners or kinks are not differentiable at that point because many tangent lines could be drawn. This can be shown by comparing the this can be shown by comparing the left-hand derivative to the right-hand derivative, okay? All right, so now we're gonna work on a little bit of curve sketching. To sketch the graph of a derivative function, we must understand that we are sketching the x value of f against the slope of the tangent line to f at x. That just goes back to that comment I was making when I first showed you our first, that x squared graph, 2x squared, whatever it was. When I was showing you the blue graph, that was the original, and then that line we got, that was the derivative function. I was saying how every point on that line was telling you the slope of the tangent of the original graph at that particular point. Note, when we are sketching the graph of the derivative of f, we are only concerned with getting the correct shape. We're not concerned about finding the exact points besides the x-intercepts, okay? So here's how we do it. To sketch the graph of a derivative function, on the original graph, draw in all the horizontal tangent lines. These lines have a slope of 0, so we can graph these as x-intercepts. Okay, so everywhere where you see a horizontal tangent line, you can put an x-intercept for your original derivative, or not the original, I shouldn't have said that, sorry, for your derivative function, okay? If the graph of f of x is increasing over an interval, the derivative will be positive. If the graph is decreasing over an interval, the derivative will be negative. Okay, so let's take a look. On each of the grids below, the graph of f of x is shown, sketch the derivative. So here's what I want you to see. Right at this point here, I know I have an x-intercept, okay? Because right there, I would have a horizontal tangent line on that vertex. Now, leading up to that, my original is descending. Well, we said that when the original is descending, my derivative has to be negative. So that means I'm going to need to be like going in that direction. Okay, and then when I'm ascending, my derivative has to be positive. So my derivative graph should look something like that. Okay. Now, the green guy is the actual one, and I was pretty darn close to the actual line. But what I would be looking for right now in your drawing is just that line. I need to see that you hit at -1, that there's an x-intercept at -1. I need to see that to the left of -1, you are negative, and to the right of -1, you're positive. Okay, so like, I guess what I'm trying to say for those of you who are like freaking out right now saying, well, how do I know how steep to draw it? This would have been a perfectly acceptable answer. That still fits everything that I need it to fit. Okay, so I'm not looking at the steepness of your derivative slope. Okay, I'm just looking that you have matched the criteria together properly. Okay. Now, spoiler alert, if you haven't seen this yet, what I also want you to notice is a degree 2 will have a degree 1 derivative. Did you notice that? Okay, let's keep playing with that thought for a couple minutes. Okay, let's try this guy. So for this guy, again, I want to figure out where my x-intercepts are. So I'm going to have one there, and I'm going to have one there. Right there, the derivative has to be 0. Okay, I was increasing up to that point, so I need to be positive. I was decreasing up to this point, so I'm going to need to be negative. And then I'm increasing up to that point, so I'll have to be positive. So from here to here, I have to be negative. Well, there's only one way to be negative and make this point hit this point, and that would be to round it off like that. Okay. Now take a look at this then. The derivative, okay, so the original function was degree 3. My derivative is degree 2, okay? And here's the actual computer drawn one if you want to see. So you see, here's the point. The one I drew kind of had a steeper slope there, okay? But it still follows the exact same thing I needed it to follow. So we're looking for the general shape, not the specificity of how quickly the derivative grows, okay? All right, you try this guy now. So this is now a degree 4. Your derivative should end up looking like a degree 3. I know that I'm going to hit at here, I'll have a 0. Here, I'll have a 0. And here, I'll have a 0. I need to be, I'm decreasing here, so I need to be negative. So it should look something like this. Okay, take a look. I'm decreasing, so I'm negative. I'm increasing, so I'm positive. I'm decreasing, so I'm negative. And then I'm increasing, so I'm positive. Okay. And then this is the actual guy. Whoops, sorry. All right, try this guy. On each of the grids, yeah, keep going. So sketch f of x. So I know I would have a 0 there because I know my tangent line there is 0. The derivative has to be 0. I am increasing, so I should be positive. Now I'm decreasing, so I should be negative. So something like that. Okay. Okay. Other notations, just as we get used to the language and speaking the language. In the first example, you found that if f of x was 2x squared minus 4x minus 1, then the derivative of f at x is 4x minus 4. If the equation was expressed instead as y equals 2x squared minus 4x minus 1, then we could express the derivative as y prime instead of f prime at x. Okay, so just a notion of we can either do it in function notation or not in function notation. Okay. Another notation called Liability notation is described as follows. Now, don't get concerned about all of the words that we're about to say. It will come as you practice this. So if y equals f of x, then we can say dy over dx is the derivative of f of x. So another way of representing the derivative is to say dy over dx, which we can also say the derivative of y with respect to x. In the second example, you found that if y equals the root of 2x minus 1, then y prime was 1 over the root of 2x minus 1. We could also say that if y equals the root of 2x minus 1, then dy over dx, or the derivative of y with respect to x, is 1 over the root of 2x minus 1. Another way to say this is d over dx of root of 2x minus 1 equals 1 over root of 2x minus 1. So we're saying here the derivative of root of 2x minus 1 is this. If you want to evaluate a particular derivative at x equals a, then we often would write it this way. So we would say the derivative of y with respect to x at x equals a. Okay? And if you had gone and played around with your calculator, that is how your calculator actually showed it to you when I gave you, oh no, it actually would go d over dx. Okay, so I don't know if you can see my calculator if I show this up to you, but your calculator does it as d over dx. So then I put the function in and then I said x equals 3 and it gave me out the derivative, okay? Liebniz notation, is good for emphasizing that the derivative is the instantaneous rate of change of y with respect to x. Okay, and then a third notation of a derivative is just saying d f of x equals d subscript x of y. Okay. Okay, so the following notations can be used for the derivative of y equals f of x. We could say f prime at x, we could say y prime, we could say dy over dx, we could say d over dx of f of x, or we could say d of f of x equals d subscript x of y. Okay, so all of them mean the same thing. We're just trying to get you comfortable with the fact that there's different ways of noting the derivative. Okay. All right, so that's it for our first lesson together. I think that's enough for you to kind of wrap your brain around. Your homework is here, and then if you have a chance, go through the next note as well, just so that you're ready for class, okay? As always, if you do have any questions, I am here and more than willing to help, so please connect with me, okay? Have fun, guys. Take care.